Well, welcome to chapter two and of our physical science course. I am going to go ahead and I hope you've been, practicing uh, things that we have talked about this far. We are going to start building on what we have been learning, and so now we're going to have some more physical concepts and some more um, the physics of some of the things that we know happens around us, but just to give it a little more scientific meaning, and of course to put in those equations and relationships in there that is a result of using the scientific method and of us understanding these phenomena better. Now, as we talk about motion in this chapter, we're going to start talking about the force, because really that's the thing we need in order to get something moving in the first place. We need to push it, we need to pull it, we need to put some force to it so that it will change its motion, right? So when we're talking about force, force is a physical quantity that that we will work with, and when we use net force in science, this net really represents the sum of all the forces. So when we have so when we have the net force, we're really summing forces in all different directions, and we're going to work that out. And if there is a net force, that it means something is going to happen, that the object is going to change its motion. If the net force is not there, if the net force is absent, if the net force is zero, then the object doesn't experience any change in the state of motion. So the thing I want you to take from this is that the net force causes a change in the motion. Force, change in motion. No force, no change in motion. So, what is motion in the first place? Motion, when we think of motion, we think of something that's moving. And when we have things that's moving, we know it's moved. Let's say you left something on your desk, and when you come back, you're like, who moved my pencil? Well, the only reason why you would say who moved it is because now it's in a new position. So moving is a change in position. So it can move 5 centimeters to the left, 5 centimeters to the right, up, down, on the floor. It has moved, it has changed its position. So when we have motion, we have a change in position from one point to another. It's now sitting in a new point after a certain time t. And we use little t for time. Now, let's think about some things about motion. If you left a cup of water on your desk and you come back an hour later and the cup of water is still at the same point you left it on the desk, has the cup of water moved? Now, that's kind of like a trick question, because one might say, no, the cup of water has not moved because it's in the same spot I left it. But in the hour that you were gone, here's something that could have happened. Your roommate might have come looking for a book on your desk or looking for something, took the cup, put it somewhere else, or held it in their hand, looked around, put the cup back. Now the cup moved, went somewhere around, and then came back to its original position. And so we say that the net motion is zero, there's because it came back to its original point. So when we're talking about motion, we're talking about the change in position after a certain time. So if it after 1 hour it's still there, its net movement was zero. But that doesn't mean it didn't move. I mean, it could possibly have stayed there, but it's also another possibility. And we'll talk about how we can describe those different possibilities, those different things that come up. All right, so we describe motion by looking at distance. So We look at distance, we talk about position. When we're talking about motion, the position has changed. The speed and velocity. Now, here's some words we have not met before. What do you understand by speed? Speed is how fast something's moving. So, in other words, it's how fast our motion is changing. And velocity is also how fast our motion is changing. So velocity is speed, but it's a special thing. It's a speed in a specific direction. And if you've ever stepped on your accelerator in the car, you know what we're talking about when we're changing our when we're accelerating, is we're changing our velocity. So we use the symbol we use for speed and velocity is V. The symbol we use for acceleration is A. So acceleration is what happens, and here's that delta we talked about in chapter 1. Acceleration is the change in velocity. But it's not just a change in velocity, it's how fast our velocity is changing. Now, our speed is how fast our position is changing. And we can use D for distance or displacement. So we'll come back to this. I'm just writing it here so we can talk about the ratios of those quantities with position, velocity, and acceleration. So when do we apply these? We apply these to horizontal motion on land, just like you're driving a car on a road. The road might have hills and we keep going in that way. We can talk about falling objects. It's you toss something up and it falls. And then there's what we call compound motion. If you've ever tossed a football, then what you have done is you've taken the ball through some compound motion. And I'm drawing this little line here. I'm going to draw a little guy. He's going to toss a football, and the football goes up and it comes back down, right? So there's two sorts of motion with this football when you toss it, and it goes up to a certain height and comes down. This is the vertical motion. You know, the football starts falling, but it's also moving in that direction. And that is what makes it a compound motion. That is what makes it two-dimensional motion, because it's moving up and it's moving out or away from at the same time. So when we want to explain motion, we would have some basic ideas behind our explanation, and these will involve forces. Like I said, we need a force for us to have a change in motion. If there is no force, the object does not change its motion. But does that mean that the object is not moving? No. It just means that the object does not change its motion. So if I'm driving and I'm going 10 miles an hour and there's no forces acting on me, I'm just going to keep going with the same motion. I will not change my motion. That's what it means. So another thing that determines how an object moves is by inertia and its mass. Now, inertia is sort of related to mass. Inertia is the resistance to motion. And so if you have your pencil on your desk and you just sort of give it a little flick of your finger like this, the pencil moves on. The pencil has a small mass and it has a small resistance to change in motion. If you do that to your textbook, it's not going to quite move. And that's because the textbook has more inertia. So we have inertia, and we know mass is the amount of stuff, the amount of substance an object is made up of. The more mass we have, the more stuff, the more substance we're made up of. And all of these things affect our motion. The more stuff we have, it's more difficult for that object to move. What we're going to come up with in this chapter is we're going to look at Newton's laws. And Newton's laws are relationships that govern motion. Like we can use Newton's laws and we can make predictions as to how something will move simply by understanding Newton's laws or applying Newton's laws. All right, so these types of the forces, inertia, mass, Newton's laws are going to help us understand momentum and impulse. And we come up to these, understand circular motion and Newton's laws of gravitation, and we can use that for explaining Earth satellites. Momentum is what we have when we're describing an object and we just want to describe the size of the object and its motion. For example, a truck has more momentum than a person on a bike moving at the same speed. So a truck in traffic at 10 miles per hour and a person riding a bicycle at 10 miles per hour, you have two things happening here. Two different masses. The truck is really, really big, so it has more momentum because it's massive. And the bicycle is really small. So if the truck and the bicycle collide, then we're going to have some things happening with that momentum, right? The thing with the bigger momentum is going to do more damages. The bike, the impulse is our change in momentum. So how fast we change momentum tells us like how much force is going to be on us. And we'll talk about these things. Circular motion describes itself. It's motion in a circle, like a satellite orbiting. And we can talk about how Newton's laws govern this motion in the circular satellite's orbit. All right, so here's our key fundamental parts of motion. We have a change in position and a change in time. So let's look at what we have here. We're looking at the clock, and it's 1 o'clock. And after 1 hour of traveling in our car, we traveled a distance of 50 meters. After the second hour, we traveled a distance of 50 meters. So if you were 50 meters from your house and you kept driving 50 meters away from your house, then after 1 hour, you would be 100 kilometers away from your house. You would have traveled that 50 kilometers. And in the second hour, you'd have also traveled an extra 50 kilometers. So at the end of our 2-hour trip, you would be 150 kilometers away from your house. So when we have this happening, look at the total time and the total distance, we will see that we can get what's called the average speed or the average motion. And since we're talking about it away from your house, I will call that the average velocity because we're going away from something. And that is the change in the distance with the change in time. And we see that the change in the distance is 50 kilometers in every 1 hour period. So guess what? Your average speed is 50 kilometers per hour. Now, does that mean that you stepped on your accelerator or you kept your foot on the pedal to maintain 50 kilometers per hour the entire time? No. Sometimes you might have had to speed up to pass a truck. Maybe other times there was traffic. All we know is in this 1 hour period of time, at the end of that hour, we had traveled a total of 50. So this is your average speed. Okay. And that's the difference. That's a takeaway here. That's not if you're looking down at your odometer or your speedometer every time, that's telling you what your instantaneous speed is. So you have average speed or average velocity, and then we have our instantaneous. And our instantaneous speed or instantaneous velocity is what's happening at that point when you look down at your meter and it tells you how fast you're going. Other than that, if you look at the total distance and the total time, we will get our average. So when we're measuring our motion, we have to look at our change in position and we have to get our change in time. And when we combine those together, we get our speed. And of course, like I said, our speed and our velocity, which is equal to a speed in a specific direction. So the thing about it is that speed is just the number. Like if I say I traveled or I drove 50 kilometers per hour today. So you know how fast I drove my car. But if I said I drove 50 kilometers per hour all the way to UCA today, then you know the direction I was heading. Or I drove 50 kilometers per hour north today. So I was driving that fast and I was heading up north. So now I've given you my velocity. There are two different things here. And there's a different kind of quantity. When we have the direction, we have something called the vector quantity. And we'll talk about that later. When we just have a size of the number, the value 50 kilometers per hour, sure, you went 50 kilometers per hour, we don't know in which direction you drove, then we just talk about our speed. And of course, when we combine that change in from our position and our time, we can get our velocity. And when it's our velocity changes, we can get our acceleration. Alrighty, so like I said, to get the speed, we take the distance divided by the time. And your average speed is the most common measurement that we will do because that's taking the total distance and the total time. Instantaneous speed is when we just look down at our speedometer. No time really has passed. We look directly at that point in time and we can determine how fast we're going. So we did this before. We calculated the average trip between of times 1 hour and 3 hours. We just calculated this example and we saw it was 50 kilometers per hour. So I'm not going to repeat that here, but technically that's the equation that we use. I went ahead and I included the delta values in front of these because I want you to know that it's the change in position. Because if you were to just write your numbers here, you would say that's 100 kilometers in 1 hour, but no, it's the change in the distance, which is only 50 kilometers. And so the answer for this was 50 kilometers per hour. All right, so like I said, we have vectors and scalars. And the vectors tell us the quantity, all of the physical quantities fall into vectors and scalars. Not all, sorry, some that we will talk about. So velocity, which is the speed in a direction, is called the velocity. And that's a vector quantity. Example, 2 meters per second due north and 2 meters per second. Only a size, no direction. All right, another thing we have, so we have velocity and the scalar equivalent to velocity is the speed. Let me put that in here. Another example of a vector quantity that we've met is we can have speed in a certain motion in a certain direction, or just an idea. Like I said, I walked 3 miles today, so you knew the amount. Or I walked 3 miles west today, or 3 miles towards the Greek church today. So then you know the direction that I was heading in. So when we have distance in a certain direction, we call that, the scientific name for that is a displacement. And when we just have the distance, you know, so this would be, for example, 3 kilometers due west. This example is just 3 kilometers. There's no direction. So here we have um, another vector quantity, displacement, and here's your scalar equivalent to that. So as we go on, we will meet other vector quantities, and in vectors, the direction is going to matter. So I have these arrows on the picture here, so they're pointing in that direction. So that matters. Force is another example of a vector quantity. So the direction of the force is going to matter whether I'm pushing to the left or pushing to the right, and that's going to matter because that's going to determine the way the object moves. Scalar quantities, we just have a size. It doesn't matter to us what the direction is. We're only concerned with the magnitude. So you might have seen this from Despicable Me, where we had that villain named Vector, and it's because he can commit a crime with direction and magnitude. So that was, if you now that you have studied what a vector is, you go back and you can rewatch that and be like, oh yeah, I know what he's talking about, and why that particular part of that movie was funny for an additional geek area to kind of snicker and laugh at if you're into that. All right, so velocity is going to tell us how fast something is moving. In addition, what direction it's going to move. We talk about these things and we represent these things graphically, where we use length as the magnitude. So in the picture here, we have a car that's moving. Oopsie, where did you go? Here we go. Hey, come back. Yeah, we have a car that's moving at 30 kilometers due east, and we see we have a short arrow pointing here. And then we have another car that's moving at 60 kilometers per hour due east. And this arrow here that's representing the velocity vector is twice as long. So this length of the arrow represents the magnitude, 60 kilometers per hour, and the arrowhead points to the direction it's heading. So if we look in this picture, both cars are heading in the same direction. Now this car coming up at an angle here, hold on, let me get the pointer. So this car that's coming up at an angle is pointing in this direction. So that's heading, we know that's the direction it's heading. It's also traveling at 60 kilometers per hour. So the length of this black line is equal to the length of this black line. The only thing that's different is in direction it's pointing. And so even though they have the same speeds, they're traveling in different directions. So these are all different vectors. These are all actually different velocities. These two cars have the same speed, but they have different velocities simply because it's traveling in different directions. If we were to turn this car around and point it in the same direction, then they'll both have the same velocity. So right now, as they're standing, they have different velocities. Now let's talk about acceleration. We said acceleration is a change in speed or change in velocity, the rate at which we're changing our velocity, because acceleration is a vector quantity. There's no scalar version of acceleration. We're always accelerating in a specific direction, which means it's the change in the velocity or the rate at which our velocity is changing that's going to give us our acceleration. So if we have a car, like with the car is traveling at 30, now we switch over it. This is from your textbook, 30 miles per hour. It's traveling 60 miles per hour. But then as the speed increases, here it's heading in that direction. our acceleration is also in this direction. Here we're traveling at 60 miles per hour, we're slowing down to 30 miles per hour. Our speed is also changing, or our acceleration is changing because our velocity vector is in the up, is getting smaller. So here our acceleration, I'm going to draw a line with the arrow showing you that. Now, the reason why we get it pointing in the opposite direction, I'll show you in a little bit here. Another way where we can change our direction is if we go around a corner. So we're traveling around a circle, for example, and we're traveling at 30 miles per hour. We can keep that speed constant, but our velocity is changing all the time. And because our velocity is changing, our direction is changing. That's why we have an acceleration, because we have a change in our velocity. So whenever we have a change in velocity, we have a change in acceleration. So let us look at how we can transfer our relationship, our law for acceleration, which is change in velocity with change in time. You see, the change in velocity can be obtained by taking the final velocity and subtracting the initial velocity. Now, usually when we're accelerating, as we're increasing our speed, the final velocity after a certain time is always going to be greater. But if we are decreasing our speed, if we're slowing down, our final velocity after a certain time is going to be less than where we're starting with, because we're slowing down. And since if this number here, if this final velocity gets less, then this small number minus vi, which is larger, is going to give us a negative number. And so when we're dealing with vectors, we use positive direction in one place, like in this case, as we're speeding up, we said, okay, heading in that direction is positive, we're accelerating in that direction. Then when we're slowing down, it becomes the acceleration becomes negative, it switches. So negative is the opposite of the positive direction, and that's how we can sort of switch our directions with that. Alrighty, where did that go? All right, so yeah. So our acceleration is, we can have a straight line acceleration, or we can have acceleration around a circle, and of course they depend on the average velocity, which is the initial and final velocities. And so here we have our average velocity and how they're related to our acceleration. All right, so let us move on to look at the relationship. So far we've talked about our speed or velocity, average speed or average velocity is distance divided by time. When we're working with these equations, we can what we call rearrange the equations so that we can get the thing we're looking for. For example, velocity is distance divided by time. So distance is equal to the velocity multiplied by the time. Or we can say the time is the distance divided by the velocity. So I want you, this is sort of like typical rearranging of equations that you would have studied in high school. And so again, if it's been a while and you kind of not quite sure, you may need to just, go over some of that on your own, review that part of your text and look it up to see how you can get up to the point where you're comfortable with doing that. So we've talked about the fact that in the SI system of units, we have meters per second. So if we're traveling at 10 meters per second, just to give you a perspective, because all cars tell us our speed in miles per hour. So if you're doing 10 meters per second, that's about a 22 miles per hour. 20 meters per second is about 45 miles per hour. 30 meters per second, 67. 40 meters per second, about 90 miles per hour. So, which, some cars are really happy to do on I-40. So we talked about this. We can change our velocity if we're speeding up or slowing down, like we saw the car moving traveling at 60 miles per hour, 30 miles per hour, then 60, or slowing down if it's traveling at 60 miles per hour, then 30 miles per hour. We can also change our velocity when we change direction, such as moving in a circle. So again, here are some different units for velocity. Note in purple here that they all have a direction, and that's what makes it different from the speed. The speed is only the number in feet per second, meters per second, miles per hour, no direction associated with it. So acceleration is the rate of change in velocity. We said some of this before. Acceleration is a vector. Acceleration, oops, here we go. Acceleration direction can be the same as the direction of the object is moving, or in the opposite direction, depending on whether the object is speeding down or speeding up or slowing down. Velocity is always in the same direction as the object is moving. Okay, so it can't move. Velocity can't be opposite to the direction it's moving. It's always going to be in the direction it's moving. The car is heading in a certain way with a certain speed in a certain direction. That's going to be our velocity. Our acceleration can switch directions whether or not we're speeding up or slowing down. If we're speeding up, acceleration is going to be in the same direction we're heading. If we're slowing down, we're going there, but acceleration is sort of pulling us back and slowing us down. Okay, so let's see if we can. You don't have any nearest neighbors, and you probably don't want to call your neighbor, but let's think about this for a second. Along the trip, an officer notices the driver in the car was in violation of a 55 miles per hour speed limit. The car travels 50 miles per hour in 1 hour. So what is the speed of the car? So if you read that as I put it up just a second ago, 50 miles per hour in 1 hour means the speed is 50. That's the speed. But is the person in violation? And the answer will be, of course, yes, because it is possible. I'm not saying, no, so retract. It is possible that the person could have a 50-mile break the 55 mile per hour speed limit, because at some point in the person's journey or in your journey, you may have to pass a truck or pass something sped up past 55 miles per hour, and sometime in your journey you may have slowed down. The fact that in 1 hour you traveled 50 miles doesn't mean that you didn't speed up or slow down in the time. It just tells us what the average is. So this thing is average, because we have the total distance and the total time, and what the police recorded was the instantaneous, and that's the different. So what three controls on your car causes acceleration? So your accelerator, your brake, and your steering, which changes the direction. Can the car's instantaneous velocity and acceleration ever be in opposite directions? Yes. This can happen if we're, like we just talked about, when we're slowing down. Now let's talk about things that's falling. Aristotle was a scientist who did some experiments on falling objects, and he said that heavier objects fall faster, and that objects moving horizontally require a continuously applied force. So when we go back to the scientific method, Aristotle just had his observation, he relied on thinking. He didn't really create an experiment to test his hypothesis. Galileo came later, and he went up on the Tower of Pisa, he dropped different objects, and then he did an experiment, and then he recorded and sort of thought about explaining what he observed and why. So together, and then Newton, who some years after that also put together the story of things falling. Now, you might have heard about Galileo Galilei, and of course, Isaac Newton is very, very famous. And you might have heard about the whole apple falling from the tree, and he saw the apple falling from the tree, and he got the idea for gravitation. So that's a legend. No one really knows if Newton actually saw an apple falling from a tree, but we do know there was an apple tree. There's actually the apple tree from his orchard that's in the Liverpool Museum right now, that where they've kept it alive, which is kind of really old and straggly, but it's still alive. Um, because it's the center of this great discovery and this great scientist. So, some of the things that Galileo and Newton put together from their experiments and their observations and testing their hypothesis is that all objects fall at the same rate and no force is required for uniform horizontal motion. And so their ideas behind what we understand about motion is based on actually taking measurements. So then you want to raise the question, well, if no force is required, how does something stop, right? If we toss something, if I push my book, why is it not moving until I apply a force? And there's a reason for that, right? It's because there's friction between your book and your desk, and the friction is also another force that's pushing against the force you applied on your book. If you had a frictionless surface, you push that book, it's going to go. If you've ever gone on ice and you tried walking on ice, you would realize that you slip and you just keep going, or your car slides, it just keeps going without you applying any force because it's frictionless. And once that object is moving on a frictionless surface, it's going to keep moving. As long as there's friction, there's going to be a hold back. It's going to be pushing a force you have to work against. And that's why things stop moving. But in reality, no force is required for that motion to continue horizontally once it's set. Okay, if the object is put on a frictionless surface, it's not going to move. We have to get it moving in the first place, but it's not required for it to keep moving if it's frictionless. Objects, however, that's falling fall at the same rate, and they observe that. So there's this sort of like a constant thing that's pulling it and making it move, fall at the same rate, and we will talk about that. So what Galileo did was he performed experiments by dropping a stone, and he found that the higher the stone is dropped, the greater the speed was when it hit the ground. So it meant that it wasn't just keeping the same constant motion, that the motion was changing, which is what we talked about. And we said if a motion is changing, what's causing it? This whole start of the chapter told us, right? If there's a change in its motion, if we set it at 10 meters per second and it keeps increasing and keeps changing that motion, it means there's a net force. So from his experiment, he sort of brought us to the fact that there is a net force, and that net force this net force is causing an acceleration, is causing that increase in the velocity, it's causing a change in the motion. So he said the velocity of the falling object was proportional to the length of time that it has been falling. So the greater the time you have it falling, the greater that velocity will be. And so how fast it's moving depends on how long it's been falling. And so we know that when we have something that's falling, and if since objects fall at the same rate, the change in velocity is happening at the same time, they have the same acceleration. And Newton came along and he worked on that and got the relationships for that, and we were able to determine that this acceleration, that gravity has a force and it causes objects to accelerate. It causes objects to speed up as they fall towards the earth. And that value is 9.8 meters per second squared. So that is the acceleration to which something falls. In English units is 34 feet per second. So when an object is falling, it accelerates. So falling objects accelerate. right? And the fact that they fall at the same rate, it means that that acceleration is constant, and it's independent of the actual size. So what do we do when we calculate net force? At the start, I told you that the net force is the sum of all the forces. So in this case, we have, a force being applied in this direction on this side of the ship, 1,000 units of force for each, maybe two tugboats pushing on a ship with 1,000 units of force. The ship moves out with 2,000. So the net force is 1,000 plus 1,000, and we can add them, they're in the same direction. Now, if we look at over here in B, we have 1,000, so one tugboat pushing in this direction and the other one pulling in the opposite direction. So if we let this direction be positive, then the opposite direction becomes negative. And so the net force, which is the sum of the forces, will be 1,000 for the one that's in the positive direction, plus negative 1,000 for the force that's in the opposite direction. So when you have a positive and a negative, remember that becomes minus or negative, and that is zero. So that's why we have a net force of zero. If we have a tugboat that's pushing in this direction with 1,000 units, and then another one pulling it over in the opposite direction with 2,000 units, then like I say, if this is positive, the opposite direction becomes negative. So in this case, the net force would be 1,000 plus, because it's the sum, but then we have to put the vector quantity for that, which is negative 2,000 because it's in the opposite direction. So it's negative 1,000 newtons, and we have negative 1,000 units. And we haven't, so we talked about negative is in the opposite direction, so it's going to move the net force in that direction. And that's how we can calculate our net force. So altogether in nature, we have these fundamental forces. And the fundamental force is, for example, the gravitational force, which is as a result of mass interactions. Of course, it controls the motions of our planets, our stars, our galaxies. We have electromagnetic forces, which is due to charge interactions, which we'll see when we study electricity and magnetism. We have the weak force, which is involved in certain nuclear reactions. And we have the strong force, which holds the nuclei together in our atom. Those protons and neutrons that we saw in that video, holding those together. That's the strong force. So those are fundamental forces in nature. Another thing we can do to look at the vector sum is to look at this book that's sitting on a table. We always have we can draw the forces on the book, and one of these things is the weight of the book. Weight is a force. Weight is the force that's due to gravity, right? Objects are falling because a force is pulling it and is causing a change in motion, and that force is the force due to gravity. And when we get the force due to gravity, we call that the weight. So your weight is equal to your mass times your acceleration due to gravity. So we have one way of getting the weight. Now, one thing I want you to make a note of here, because this happens every semester, people confuse mass and weight. So mass is in kilograms, and it's the amount of stuff we're made up of. Weight is a force due to gravity. It's not amount of stuff. It's the amount of stuff times the acceleration due to gravity. And the unit for that is in newtons from Isaac Newton. So the book doesn't fall through, even though it's pulling it down, because the table exerts a normal force on the book, which is from Newton's third law of motion. And so when we add that up, the sum of uh, the vector sum will be equal the to zero. All right, so falling objects, if an object is falling, the distance that it falls is given by this equation, 1/2 at squared. A is the is the acceleration downward. And of course, if it's falling, that's equal to g, gravity, which is 9.8 meters per second squared. So the distance traveled as it's falling down is 1/2 times 9.8 times t squared. So that distance, 1/2. Right, and this is only for falling. This is not for moving in a constant direction, right? Um, if an object is moving, if it's not falling, we'll talk about that in a little bit. All right, another thing we talk about when we talk about motion is the one jumping up and down motion. So in basketball, I am told that people would brag about having a hang time. People claim to have 2 or 3 second hang time, when in reality, the distance is equal to 1/2 um, gt squared, which is 9.8. So let's say someone says that their hang time is 3 seconds, then let's see how high they will jump. If it's 3 seconds, it means that it's 1.5 seconds up and 1.5 seconds down, because they're we'll assume that it's same time going up, same time coming down. So it's 1/2 times 9.8. And that's only, so if it's 1.5 seconds, if it's a hang time of 3, then 3 divided by 2 is 1.5, because it's halfway up the trip to reach its highest point. So 1/2 times 9.8 times 1.5. And I'm going to plug that into my calculator here. And we can calculate, and you can do this too, as I'm doing it. Make sure you get practice using your calculator to do these kinds of problems. 0.5 times 9.8 times 1.5, and we have to square that. All right, so with this, it tells me that 11.02 meters. Now remember, a meter is about a yard. So someone who brags about the hang time of 3 seconds, like I'm 3 seconds in the air, that means they took 1.5 seconds to reach their highest point. They're saying they can jump up, you know, one level of floor in a house is about 10 meters. So they're jumping almost the height of one-story building, which isn't quite true. But that's how you can use science to explain some of that. All right, so when it comes to falling objects, we can get, I don't know if you can see this, d is equal to 1/2 a, and I'm just going to write g here because it's acceleration due to gravity when it's falling, d squared. Okay, so let me just erase that. Maybe that's why it wasn't. Hello. Let's get eraser and clear this up. Right, so objects that's falling is going to fall at a constant rate. And so we have an object that's released here. And let me get a laser. And so we can see how the distance changes every second using our equation as the object falls towards the ground. When it comes to compound motion, we have horizontal and vertical motion combined, such as an object thrown in the air. And the thing about it is that gravity acts all times, and gravity is only affects the vertical motion. It doesn't affect your horizontal motion. So acceleration is independent of the object's motion. So the acceleration is always there and only affects, the acceleration is only going to affect the downward. It's not going to, there's not going to be any acceleration horizontally for that object. All right, so as we have vertical motion, the object slows down. If you toss something up in the air, it's going to slow down. It's going to come to a stop at the point at the top, and then it's going to start speeding up and fall back down. And that's where the acceleration is going to happen. And the reason why it stops is because as it's moving, upwards, and there's our velocity upwards, we have all the time acting on us is the force due to gravity. So acceleration is always towards the earth. It's always pulling it down. And it's kind of like a car slowing down, right? It's moving in that direction. The acceleration is the opposite direction. And so it starts slowing down because of gravity. It comes to a stop and then it starts speeding up as gravity pulls it down. When we talk about horizontal motion, the velocity is the same, assuming there's no air resistance, because air resistance is what's going to affect the motion. But there's no force acting on it like we have the force due to gravity. So that curved part, so the object starts traveling up, but then it's also traveling out. So it makes that sort of a curved path as you see here. So we have this arrow that's fired. So, in this first picture, the girl shoots the arrow out and it's going horizontally. It's going to keep at a horizontal motion, but then the gravity starts pulling it down, and that's what makes it come down. So it's going to travel the same time, the same distance as it normally would horizontally. Remember, our distance is equal, our velocity is equal to distance divided by time, which means our distance would be whatever speed she shot it out multiplied by time. So however long, that'll be the distance that it travels horizontally. Vertically, however, we have it speeding up, right? So it travels a different distance. Compared to if we just release it, it just falls. There's no horizontal motion with that. So in picture B here, the guy isn't shooting it out, he's just dropping it to the ground. So when you tossing a football, the player is going to toss the ball. It's going to go up, but because of gravity, that speed is upward speed is going to slow down, and eventually it's going to come to zero. It's going to keep moving horizontally. If you look at the size of that arrow, the horizontal arrow is the same length because that stays the same. The only thing that's changing is the vertical motion.